Hello students, this is Rishabh Anand from Perfect Academy Physics faculty, and today we are going to discuss kinetic theory of gases, which is say part of thermodynamics. After that we will go to the thermodynamics. So before that we have to study the kinetic theory. That means the movement, the random motion of gases and analysis of that random motions. Because as you say, this kinetic theory is basically analysis of gases in random motion. So, and you know that gases, they travel and they have very less intermolecular forces, so they have random motions, which you will see that is called the Brownian motion. So before that, we should know that gas follows this gas law, right? Gas law, where this is pressure, this is volume of container. Why? Because in any container, when you take, because of gases and the random motions, they occupy all the available space. So volume of gas is same as volume of container. N is moles. This is universal gas constant, and this is absolute temperature measured in Kelvin scale, so K. So this is the gas law which every gas follows. Okay. Now, from this we have different modifications also, but before that we have to make some certain assumption to define ideal gas. That means to define ideal gas we have to make some assumptions. It is very important to take assumptions. Now, first assumption is, if you say here what you look, volume of container is same as volume of gas. That means they have that molecule of gas has very negligible size compared to the container, and we can actually know this thing and we can understand easily the molecule of gas is very negligible compared to size of container. That means if a particular molecule is there and this is the container, but this molecule cannot be defined where to go, so it will have different movement. Okay, so they occupy the whole volume. That is why we have volume of container equals to volume of gas. Second assumptions. Second assumptions, between molecules there is no intermolecular interactions. That means there is no interaction, no attraction, nothing, and they are in very large separation. Say here, the distance between two molecules are very large. Say M1 and M2 are gas molecules. So compared to their size, this distance is very large. So there is no intermolecular interaction, and that is why we defined potential for the ideal gas as 0. So potential is 0. Okay. Now, next. When several molecules are there inside a chamber, a container or a vessel, they collide with each other. Okay, and we consider that collision as elastic collision. Okay, so between any two molecule collisions are elastic. Collisions are elastic. Plus, they have the time of collision is very small because there will be a successive collision. If I say three molecules are there, they here collide, and then this is colliding here in this particle. So if T1 is time, T and T2 is time between the successive collisions, but the time of collision when they are coming near, that means you say that time of collision between molecule is very less compared to time of the successive collision. It means time taken to collide with another molecule is very larger than the time of collision between the molecule itself. Okay, so this was one of the assumption. Now, fourth assumption. And because of this collision, they collide with walls also. Container walls, they collide with walls. And because of that elastic collision, there is change in momentum with the velocity, or change in momentum with collisions. And because of that change in momentum, there will be a force, because change in momentum is with time is force. So force upon a particular area gives you pressure. That is why gas exert pressure on container. We'll see that later. Now, fourth is they have Brownian movement, or they have Brownian motion. That means a random motion. Like we cannot define direction of motion of gas, where they will go. Like several gases particle, if I assume here, so this gas may go like this, then they collide here, they come here, they go there. So you cannot define direction of the gas molecules. That is why they are called random motion, and that motion is given by Brownian, and that motion is called Brownian motion. Okay, and the thing to remind in this is, between a collision, successive collision, like this part going from here to here, say suppose from A to B, the path will always be a straight line. Path will always be a straight line, because we don't consider here the effect of gravity. Okay, remember that we don't consider the effect of gravity. That is why the motions are in a straight line. Always, it cannot go like this and collide with another particle. Okay, because this is a parabolic shape coming because of the gravitation. So there is no gravitation, no effect of gravity. All the motion are straight line motion. Fifth, we consider all the molecules as spherical and rigid. All the molecules are considered as spherical and rigid. Okay, and sixth, they follow Newton's law. They follow Newton's law of motion. So these are the assumptions taken for ideal gas. Now, let us go to topic of pressure exerted by gas on container wall. Okay, let's say I take a cubical container. Okay. Now, if I say this length L, this height H, and this B, a particular molecule is there inside having random velocity, say V. Then this velocity can be have in components form like Vx, Vy, and Vz. Now, if I consider only the x direction, okay, then it has Vx speed. So now, so this area, this part of area, B into H area, this molecule is going to strike. So we write first going momentum to strike this wall is mvx. After striking that wall, it returns back, and collisions are elastic always, with walls also, with in between the molecules also. So they return with the same velocity mvx, but we say minus because changing direction of velocity. So net change in momentum, you write mvx minus of minus mvx, that is 2mvx. Okay, if you want to give vector sign, then I can. In magnitude wise, delta p is 2mvx. Now, to strike that wall, first it will take time. First time, say, to strike that wall is L upon Vx. Okay, L upon Vx. Second, so to again strike that wall, it will take again the same amount of time. Coming back, striking L upon Vx and coming back, it will take same time. So second time to strike will be same as L upon Vx. That means total time you can say to strike, to have successive collision, okay, delta t average time is 2L upon Vx. Okay. Now, so average force imparted by that molecule on container wall, you will write change in momentum, which is 2m Vx upon 2L upon Vx. That means m Vx whole square. Okay, that is the average force given by one molecule, and that m, whatever we are writing m is mass of one molecule. Okay, now to write pressure, average pressure because of one molecule, what will be F average, force upon area. So this is mvx square upon, sorry, here L. Area which is striking is B into H. So B into H, which is mvx square upon volume of container, LBH, volume of cuboid. Okay, that means we say that P average along X is mvx square upon V. Okay. Now, similarly, we can write for Y and Z also. And Vx square, all Vy square, and all Vz square will be same. That means if you write for P average along Y, you will write mvy square upon volume V. Then for Z also as mvz square upon V. So total average will be, you can write 1 by third, because you can write Vx square or Vy square or Vz square as mean of Vx square plus Vy square plus Vz square. So 1/3 of m upon V into Vrms square. We say that term as Vrms square. Okay, Vrms is given as V square upon n. Okay, so we'll deal with later this one. That is written as 1 by 3 m by V Vrms square. Okay, or how to get that is you can write Vx square as 1/3 of Vx square plus Vy square plus Vz square. Okay, you can write Vx square like this also. Okay. So P average by one molecule is 1/3 m upon V Vrms square. For a good definition, we can write Vrms as n1 V1 square plus n2 V2 square and so on by n1 plus n2 plus n3, and this RMS is root mean square speed. Okay, now that was for because of one molecule. So one molecule, you can say n1 n2 n3 all become 1, so v1 square plus v2 square plus v3 square by p. Now see here, for n number of molecule, if you take n number of molecule, you will write p equals 1 by 3 n into m upon v Vrms square. Okay, so this is because of n number of molecule, and mass of one molecule into n number of molecule, you can say that is mass of whole gas, and mass of whole gas upon volume becomes density. So also this we can write 1 by 3 rho Vrms square. Okay, now, and how will you write for n moles? See, we can do here modifications again. If it is 1 by 3 and we divide this term with Avogadro number and multiply with Avogadro number, then here Vrms square. So this n upon this will become number of moles, and mass of one molecule into Avogadro number will be molar mass. So this will be 1 by 3 n molar mass upon volume into Vrms whole square. So what will get from there? So you got P as 1 by 3 n m upon V Vrms square. Now if you write PV, this will be 1 by 3 n m Vrms square. So PV you can write as nRT from the gas law, and this is 1 by 3 nm Vrms square. So n gets cancelled and you will get Vrms value as root of 3RT upon m. Okay, root of 3RT upon m. And from this equation you can see that for a particular gas, Vrms is proportional to root of temperature. That means increased temperature will increase the value of Vrms. Increasing value of Vrms, you can increase the pressure. Okay, because of that kinetic energy taken by the gas. Now, also understand that if there is no potential for gas, ideal gas, that means all the energy taken in terms of kinetic energy is total energy for gas, because V is 0 for ideal gas. This is important. Okay. Let us discuss about some gas laws. And now, so pressure of the gas you have found, dependency of gas, pressure or density you have found. Okay, before going to gas laws, one thing you consider that if you write kinetic energy, you write 1 by 2 mv square. For gas, you can write half m Vrms square, where mass is the m is the mass of gas. Okay, and you know that pressure is 1 by 3, right? M upon V Vrms whole square. Now, do some modification. You can write P into V as 1 by 3 m Vrms square for that one molecule of gas. Now, what we'll get here is, from equation A and equation B, you can see if you take ratios, it will be kinetic energy of gas upon PV is 1 by 2 m Vrms square upon 1 by 3 m Vrms square. So you cancel the common terms, you will get 3 by 2 PV as kinetic energy, or you can write pressure as 2 upon 3 kinetic energy per unit volume. This is also important term, you should know that pressure is 2/3 of kinetic energy per unit volume of a gas. Okay. Okay, let's start with the gas laws. So, first gas law is Boyle's law, and these gas laws are given at a particular temperature and particular amount of gas. Okay, and this Boyle's law says that at constant temperature, P is inversely proportional to V, which you can see from the gas law as PV equals to nRT. When T becomes constant, PV becomes constant. That means P becomes proportional to 1 by V. So P is proportional to 1 by V. That means you can write P1 V1 equals P2 V2 as a general case, or equals to any constant, or you can write simply as P1 V1 equals to P2 V2. Now see, let's see the graph behavior. When I draw graph of pressure versus volume, so this graph comes like this. This is rectangular hyperbolic shape, so the graph is like this. Similarly, when you try to get behavior with pressure and temperature, we know that temperature is constant, so there will be a constant graph, but here pressure is decreasing, so arrow will be like this, pressure is decreasing. Now, try to draw graph of V and T. Now what will happen here? Again temperature is constant, but here arrow is different, volume is increasing, so volume is increasing. So this is PV curve, this is called PT curve, and this is your VT curve regarding the Boyle's law.